Alright, today we're going to learn about ionic bonding. So here's an example of some sodium chloride, and you can see this crystal, rock crystal over here, so rock salt. So the nature of the ionic bond, so atoms don't just spontaneously spit out electrons. It's not like you're going to find them randomly generating those. But when you have something like an electron-hungry atom, such as, say, chlorine, when it gets near an atom with loose electrons, say like sodium, the electrons can be transferred so that basically each atom will get a full valence shell. And we're going to see how that transfer takes place so that the one from the sodium will get transferred over to chlorine. And we'll learn about writing the formulas here today. So in terms of ionic compounds, these are compounds in which your particle, each particle is held together by electrostatic interactions. So if you have your positive ion and your negative ion, as they come together, they'll form a bond. And this bond is what we call our ionic bond. So that attraction between oppositely charged particles will give you your ionic bond. Here's an example of looking at your sodium and your chlorine. And if you look at a unit cell of your sodium chloride, it's in this expanded lattice structure with alternating charges of Na plus and Cl minus bonded together with ionic bonds between each of them. So in terms of your chemical bond formation, if we look at this example of taking sodium, so if you remember, sodium is in group 1, meaning it has one valence electron as shown by the single dot. Chlorine is in group 7, meaning it has 7 valence electrons shown by the 7 dots around it. So if that electron-hungry atom in chlorine, which has 7, gets near sodium, which has 1 that's less hungry for that, you can think of your electron is going to get stolen over to chlorine here. And in doing so, you form an Na plus ion, so plus 1 charge, and your chloride ion of a minus 1 charge. And in doing so, when they bond between them, essentially your Na will get close to the Cl, and they'll form this ionic bond between them of a Na and a Cl. So let's have you guys try one with lithium and fluorine and see what happens when those two react if they came near each other.
Remember, when you're using ThinkerBuddy, you need to stop and actually work through the problem, and then we'll come up with the answer.
Yeah, so it's a good time to pause and try this out. Alright, so if we take a look at lithium, you can think of, well, lithium, we can draw out its elemental symbol Li, and thinking about lithium, it's also in group 1, meaning it would have 1 valence electron. Fluorine, you can draw out F for fluorine. And thinking about this, it's also in group 7, meaning it has 7 valence electrons. So we can draw 7 around fluorine. Now thinking about which one wants the electron more, well, if fluorine has 7, it needs 1 more valence electron to become like neon. And lithium would rather lose the 1 valence electron. So your fluorine here is going to steal this 1 electron, transfer it over, and in doing so, your lithium becomes a plus 1, and your fluorine becomes a minus 1. And if we write that together as they're bonded, you would get LiF, because a plus 1 and a minus 1 would pull those together and form your ionic bond. So when an ionic compound is formed during this electron transfer process, it basically forms a crystal lattice. And a crystal lattice is sort of this 3-dimensional extended array, which we'll look at a couple more examples of. So this repeating structure of ions, you can't really find a single molecule in there. It's this big giant structure. So when we dissolve it, we'll also find that they can separate into ions as individual species. So this is a physical process, a physical property of dissolving. So here's an example of a crystal lattice. And a crystal lattice, I'm going to think of the simplified formula of NaCl we'll find is your formula unit. And formula unit will work for any ionic compound as sort of that simplest ratio. And if you look up in your structure here, you're going to find if you have this green chloride ion, it's going to be surrounded by all Na plus ions. So the opposite charges sort of touching each other. So here.
So does that mean you've got 6 sodiums for every 1 chloride?
No, if we look at the simplified ratio, what we're going to find is that you'll have 6 NAs for every 6 CLs. It's just that to represent in the structure, they'll be touching 6 of the opposite, but they'll all have a 1-to-1 ratio because of a +1 to a -1.
So all those big ones surrounding the sodiums are also chloride ions.
Exactly. So these green ones here are also chloride ions. So each one would all be touching the sodiums and keep us in that same ratio. So here's some examples of some different ionic compounds. You can see different crystal structures. And here's looking at these sort of extended 3D lattice structures, a couple others. What you'll find with ionic compounds, one of their physical properties is that they have very high melting points. And here you can see for NaCl the 804 degrees C, for MgO 2800 degrees C, so very, very high.
I've never melted salt on the stove. I've dissolved it in water, but I've never melted it.
Yeah, it'd be pretty hard to do, but maybe you could try it sometime without burning down your house.
I'd probably burn my house down, John.
Yeah, maybe not a good idea.
Okay.
All right, so if you recall back to what we've talked about previously, we have the atom being the smallest particle of an element that has the chemical properties. And an element is essentially that matter that's composed of only one type of atom. So element is a scoop of atoms. Molecule is the smallest unit of compound that has its composition and properties of that compound. And a compound here, you can think of a molecule as a scoop of that compound. So a compound is composed of 2 or more types of atoms chemically combined in proportions. And when we're talking about ionic compounds here, we're usually referring to a formula unit. So if we look at some formulas of ionic compounds, so what we're going to find here is that your compounds are always electrically neutral. So they're going to always form in opposite charges to the right amount to give an electrically neutral compound. So if we look at this example of sodium chloride again, well, we can think of sodium here. We saw in the previous example it had 1 valence electron because it was group 1. So it had a +1 charge when it loses that 1 valence electron, versus chlorine being in group 7 needed that 1 valence electron to become like argon, making it a -1. So if we have a +1 and a -1, if we add those 2 charges up, we'll see that we come out with a neutral compound of 0. Oops, I just wrote over that. So we'll do some more examples and see how to do that, but all of them always need to balance out and be electrically neutral. Wow, now that's a lot of complex formulas we got going on down here. So at this point, we haven't gone over the examples, but we'll get to do a bunch, and then eventually you guys will get to do the harder examples like these ones seen below. So in terms of writing some ionic compound formulas, we have some general rules. First thing is that cations, the metal ions, usually the basically positively charged ions, are written first. So those are all the positive ions. In an ionic bond, most have a metal present. There are some exceptions, like acids will have an H+, which is a cation. You'll also see ones like with ammonium, the NH4+. Then after you've written the cation, then you'll write your nonmetal anion, or some form of anion written next, because the net charge on a compound is going to be 0. So all your positive and your negative must cancel out to give you 0. So if you have large amounts of positive, large amounts of negative, we got to figure out how many we need of each to give us overall of 0. All right, so if we take a look at an example of writing an ionic compound formula and see how we can come up with one of those. So if we take, say, magnesium, just Mg, and chlorine, we can think of as Cl. Now if you think about Mg is in group 2, meaning it wants to lose 2 electrons, and when it loses those 2 electrons it becomes 2+, and chlorine is in group 7, meaning it wants to gain 1 electron to become like argon, so it's going to be a -1, so we can write it just as a minus or a -1. So now if we want to figure out how many magnesium and how many chlorines do we need to have in order to get a neutral ionic compound, because everything wants to remain neutral. So what we can do is we can introduce this method. It's called the loop and swoop method. So you can take your charge +2 and loop it down in terms of just the number. And then you can take your -1 and swoop that down in terms of behind magnesium. So when we do this, this will then tell us how many of each atom we need to have a balanced ionic compound with no charge. So in terms of Mg, we can think of, well, Mg, when you write it, would have a 1 here, which we'll talk about as implied and we can remove later. And a chlorine behind it would have a 2 here. Now we never write the charges down in the subscripts or in this part of the formula, so we only write the numbers down there. Now in reality, 1s are implied, so the simplest way to write this would just be MgCl2, and because there's no 1 written behind the Mg, we know that it's a 1, it's an implied 1. So let's prove this and make sure that our charges are balanced. So if we take this, we can think of, well, each magnesium we know is a +2, and we only have 1 of those, and each chlorine is a -2, or a -1, sorry. So if we have 2 chlorines, and we have each one is a -1, we can think of when we add these up together, we get a total of 0. So in order for this MgCl2 to be electrically neutral, you need 1 Mg2+ and 2 Cl- to give you 0. Alright, so one other example we'll look at. So aluminum, you can think of aluminum as in group 3A. So writing out aluminum, it would form a +3 charge, 3+. And if we take a look at oxygen, oxygen's in group 6A. So it would form a 2- charge. So if we do the same kind of thing, we can use our loop and swoop. So we can take your loop and take your swoop. And then when we come over here, so we'd see the Al basically would have a 2 written behind it, again without the charge. O here would have the 3 written behind it. So, and we can see that this is simplified. There's no 1s. We can't reduce down any. So if you think about if, again, each one of these aluminums was a +3, so you had 2 aluminums that were each +3. And you think of 2 times +3 is a +6. And then we have 3 oxygens, and each oxygen is going to be a -2. So if we have each oxygen, 3 times a -2 gives you -6. So +6 and a -6 ends up coming out 0. So overall, your ionic compound formulas will always be electrically neutral or 0. So here is another method of looking at creating your formulas of ionic compounds that we'll call the switch, drop, and reduce method. So again, if we look at aluminum, like we just saw, aluminum has a 3+, O has a 2-. So if we switch the numbers, it's basically just taking your 2 from your oxygen and putting it down here, 3 from the aluminum, putting it up here. Then what we can do is drop those numbers down, so basically moving them down to where they're a subscript, and then reducing. So in this case, 2 and 3 are already reduced. We can't reduce them down any smaller. Now if we look at calcium, so calcium is a +2 charge being in group 2. Oxygen will form a -2 charge being in group 6. So if we switch the numbers, we're going to find, again, the 2 from the oxygen will get switched over here. The 2 from the calcium get switched over here. If we drop them, you can see Ca2 and O2. Well, now when we reduce, this will be a case where if they're both 2's, we can divide each of them by 2 and get them reduced down to essentially a 1 and a 1. So now we don't have to write out Ca1O1. We just write out CaO to represent there's 1 of each. So those ones again are applied. Now in terms of your last example, so here's calcium with a nitrate. So calcium 2+ is again from group 2A. Nitrate anion, one of your polyatomics, is NO3-, so it forms a -1 charge. So if we then do this of switching the numbers, you can think of, well, 1 goes over here from the nitrate, and then the 2 from here goes over to where you're up behind the NO3. When we drop the numbers down, you can see you get Ca1NO3 and reducing, well, we can essentially leave this now as CaNO3. Now one question is, why do we have these parentheses here? What do the parentheses mean? Well, if we instead forgot the parentheses and wrote CaNO3, if someone saw that, they would think, oh wow, this is a compound that has 32 oxygen because there's a 32 behind an O. So that's going to be much different than if you have parentheses to denote. We don't have 32 oxygen, we have 2 sets of nitrate ions for every 1 calcium. So when you have a polyatomic and you have multiples, make sure you draw in these parentheses to denote that it applies to that whole unit and not just to the last atom. Alright, so we're going to do some examples of looking at formulas of compounds, and what we want you guys to do is take a minute and combine every cation with every anion. What you'll find is you'll have 3 cations, 3 anions, so a total of 9 examples that you can come up with. So take a minute and pause the video, and then we'll go through a few examples on the next slides before we show the final answer. Alright, so the first example we're going to look at is we're going to look at taking potassium, so K+, and we're going to combine that with our CO3 2-, so our carbonate polyatomic. So similar to our method that we learned before, so we can first write your K and your CO3, and then thinking of taking your number, so over here we're going to have 1 up above the CO3, and then taking this number, drawing it down, you're going to have a 2 up above the K. So then if we do our drop method, so K, if we drop down that 2, and then here CO3, we drop down the 1. Well, In this case, there's only one polyatomic, so we don't have to write the parentheses. You don't want to put a 31, you just have one of those carbonates. So this would be the example for K2CO3 in order for that to balance out and be electrically neutral. All right, the next example we're going to look at is one involving calcium. So we're going to do Ca2+, and then we're going to look at the phosphate anion, so PO4 3-. So again, we can use our switch, drop, and reduce method. So if we switch behind the calcium, we're going to put that number 3 over here coming from the phosphate. And if we switch the one from the 2, we can put this over here, again not leaving your charges. Then if we go to the drop, so Ca, so if we drop that 3 down, we get 3 here. Now here's a good example where you're going to have multiple PO4s. So here when you write your PO4, to distinguish that we have 2 of those whole phosphates, we have the 2 with this parentheses. We have to have that parentheses denote that there's 2 polyatomic phosphate ions, and we can't just leave it as one there. All right, so the last example we're going to take a look at here is manganese, so Mn plus 7, and then our phosphate, so PO4 3-. Okay, so we can do the same kind of format of having your manganese and your phosphate written. And then if we take our switch and we take the 3 and switch it down over to here, and then we take our 7, switch it over to here. So what we're going to find is if we do the drop, so we'd end up with Mn with the 3, and then the PO4 here. So remember, we have multiples, we got to do parentheses, and then 7. So all of these are different examples, and now if you've gone through the rest, you can take a look at, see if you got them right, and you can check your answer for those 9 combinations. So here's all the ones with potassium, all the ones with calcium, and all the ones with manganese. So that's the lesson on ionic compounds and writing formulas. Next we'll be looking at naming.